Most people think reality is simple. You're sitting in a chair right now. That chair exists whether you're looking at it or not. The walls around you are solid. The floor beneath you holds you up. When you close your eyes, the world doesn't disappear. It just keeps going. That's how things work. Cause leads to effect. Objects have properties. The past is fixed. The future hasn't happened yet. These aren't beliefs. They're obvious facts about existence itself. But there's a problem with that certainty, a crack in the foundation so deep that when you really look at it, it doesn't just challenge physics. It challenges the very idea that reality is a thing that exists independently of observation. And the strangest part, this isn't philosophy. It's not speculation. It's what the experiments actually show. Real measurements, repeated thousands of times in laboratories around the world. The results are consistent, they're verified, and they're absolutely terrifying because they suggest something most people would never accept. That reality might not be real in the way we've always assumed. The paradox we're going to explore doesn't have a catchy name like Schrödinger's cat. It's not taught in intro physics courses. But among quantum physicists who work at the edge of what we understand, it's considered one of the most disturbing findings in modern science. Because unlike other quantum weirdness that only shows up in carefully isolated lab conditions, this paradox strikes at something more fundamental. It questions whether the universe has definite properties at all before someone looks. And when I say someone, I don't mean a detector or a measuring device. Those are just extensions of the same problem. I mean an observer, a consciousness, you. Here's what makes this paradox different from the usual quantum strangeness. Most quantum effects, weird as they are, don't seem to directly involve human observation in a way that matters. Particles in superposition, entanglement, tunneling, these happen in systems we can describe mathematically without worrying too much about who's watching. But this paradox is different. It specifically involves what happens when observers themselves become part of the quantum system, when the boundary between the experiment and the experimenter dissolves. And when that happens, something breaks. Not the math. The math works fine. What breaks is our ability to say what's actually real. The setup is deceptively simple. You take quantum mechanics, which already tells us that particles don't have definite properties until measured. Then you ask a question nobody thought to ask seriously until recently. What if the observer making the measurement is also in a quantum superposition from someone else's perspective? What happens then? Can two observers both be right about what they measured if their observations contradict each other? And if they can, what does that even mean? The answer, according to both theory and experiment, is yes. Two observers can measure the same quantum system and get results that are incompatible with each other. Not because one of them made a mistake, not because the equipment malfunctioned, but because from their own perspectives, they're both correct. Reality itself splits, depending on who's asking the question. That's not a metaphor, that's what the paradox demonstrates. Now, before we go further, let me be absolutely clear about something. This isn't about interpretation. It's not about whether you prefer Copenhagen or many worlds or Bohmian mechanics. Those are frameworks for making sense of quantum mechanics. This paradox exists regardless of which framework you choose. No matter how you interpret quantum theory, you still have to deal with the fact that observers can disagree about objective physical facts and both be right. And that should terrify anyone who cares about what truth means. Think about what that implies. If reality depends on the observer, then there's no single objective universe that we all share. There are only perspectives. Your perspective, my perspective. And those perspectives might describe completely different histories of the same event. Yet somehow, we manage to communicate. We agree on most things. The chair still feels solid, but according to quantum mechanics, that agreement is contingent, fragile, and at the quantum level, it completely falls apart. This is where scientists start getting uncomfortable, because physics has always been about finding objective truths, laws that apply everywhere for everyone, regardless of who's looking. But if observers can have fundamentally different realities, then objectivity itself becomes questionable. What are the laws of physics, laws of if reality changes depending on perspective? Are we describing the universe or just our interaction with it? And if it's the latter, what does that say about everything we think we know? The paradox we're about to dive into forces these questions into the open. It doesn't let you ignore them or brush them aside as philosophical distractions. Because the moment you take quantum mechanics seriously and apply it to observers themselves, you get results that are mathematically sound, experimentally verified, and philosophically devastating. Two people can look at the same quantum event and record different outcomes. And quantum mechanics says they're both right. That's not a paradox in the sense of a logical contradiction. It's a paradox in the sense that it violates everything we thought we knew about how reality works. And here's the worst part. We can't just dismiss this as a thought experiment anymore. In recent years, physicists have actually tested versions of this scenario. They've created situations where quantum observers, represented by particles or detectors, record conflicting information about the same system. And the results match what the theory predicts. Reality really does depend on who's measuring it. The universe doesn't have a single story, it has multiple stories, and which one you experience depends entirely on where you're standing in the quantum web of observations. So that's what this video is about, not surface-level quantum weirdness, not particles in two places at once. We're going deeper into a paradox so strange that it calls into question whether objective reality exists at all, whether the past is fixed, whether facts are universal, and most disturbingly, whether you and I are even living in the same universe when we look at the same quantum system. The implications stretch beyond physics into epistemology, metaphysics, and the very nature of existence itself. And once you understand what this paradox really says, you can't unknow it. The world starts to look different, less solid, more uncertain. Because if this is true, then everything we think we know about reality might be nothing more than one possible story among infinitely many others. Let's begin. Before we get to the paradox itself, we need to understand why observation matters in quantum mechanics at all. Because in everyday life, observation is passive. When you look at a tree, you're not changing the tree. Light bounces off it, hits your eyes, and your brain processes the image. The tree was there before you looked. It'll be there after you look away. Your observation is irrelevant to the tree's existence. That's common sense. That's how classical physics works. And that's exactly what quantum mechanics says is wrong. In the quantum world, observation isn't passive. It's an interaction. And interactions change things. When you measure a particle's position, you're not just discovering where it was. You're forcing it to have a position. Before the measurement, it didn't have one. Not in the sense that you didn't know where it was, in the sense that the question, where is it, didn't have an answer. The particle existed in a superposition of all possible positions simultaneously. Your measurement collapsed that superposition into a single outcome. You didn't reveal reality, you created it. This isn't speculation, it's what every quantum experiment demonstrates. Take the double-slit experiment, the most famous demonstration of quantum weirdness. You fire electrons one at a time through two slits. If you don't measure which slit each electron goes through, you get an interference pattern on the screen behind the slits. The electrons behave like waves, passing through both slits at once and interfering with themselves. But the moment you add detectors to see which slit each electron actually uses, the interference pattern vanishes. The electrons behave like particles, going through one slit or the other. Same electrons, same apparatus. The only difference is whether you're watching. And that difference completely changes the outcome. For decades, physicists tried to explain this away. Maybe the detectors disturb the electrons. Maybe there's some physical interaction we're not accounting for. But no matter how carefully you design the experiment, no matter how gentle you make the measurement, the result is the same. Observation changes the system, not because of any mechanical disturbance, but because measurement is fundamentally different from not measuring. The universe behaves differently depending on whether information is extracted from it. Now, that's already deeply weird, but for a long time, physicists could live with it. They could say, okay, quantum systems are fragile. Measurement collapses the wave function. We don't fully understand why, but we can calculate what happens and make predictions. The observer is outside the quantum system, looking in. We're classical beings studying quantum objects. There's a clean boundary. We're here, the quantum stuff is there. That boundary let physicists avoid the hardest questions. Questions about what counts as an observer. Questions about whether consciousness matters. Questions about whether reality exists when nobody's looking. But here's what changed. In recent years, physicists started asking what happens if you treat the observer as a quantum system too. What if there's no boundary? What if the measuring device, the scientist, the laboratory, everything is quantum mechanical? Because if quantum mechanics is truly fundamental, if it describes reality at every scale, then there shouldn't be a special classical realm where observers live. Everything should follow quantum rules, including us. That question opens a door most physicists would rather keep closed, because the moment you make the observer quantum mechanical, everything gets vastly more complicated. If the observer can be in superposition, then what does it mean to say they measured something? From whose perspective did the measurement happen? If I'm watching you measure a quantum system, and from my perspective you're in superposition, then you haven't made a measurement yet. But from your perspective, you have. You saw a definite result. So which is it? Did the measurement happen or not? This isn't just a theoretical puzzle, it has real consequences. In 2019, a team of physicists published a paper that demonstrated this exact scenario in a laboratory. They created a situation where two observers, represented by quantum systems, measured the same event and recorded contradictory results. Observer A saw outcome X. Observer B saw outcome Y. Both measurements were valid. Both were correct within their own reference frame. But they couldn't both be true in any objective sense. If reality is a single consistent thing, then one of them has to be wrong. Except quantum mechanics says they're both right. This result sent shockwaves through the physics community, not because it was unexpected, the math had predicted this for years, but because seeing it actually happen in a lab makes it impossible to ignore. You can't just say it's a thought experiment. You can't dismiss it as philosophy. It's physics, real, measurable, repeatable physics. And it tells us something absolutely devastating about the nature of reality. The conclusion is inescapable. If quantum mechanics applies to observers, then there is no objective reality that all observers share. There are only observer-dependent realities. What you see is real for you. What I see is real for me. But there's no guarantee those realities are compatible. In fact, quantum mechanics guarantees that sometimes they won't be. We're not living in one universe with multiple perspectives on it. We're living in multiple, overlapping realities, each equally valid, each telling a different story about what happened. This goes far beyond anything Einstein worried about when he said God doesn't play dice. Einstein was concerned about randomness and determinism. But this paradox is worse. It's not just that outcomes are probabilistic, it's that the outcomes themselves are relative. Truth becomes observer-dependent, facts become subjective. Not in a wishy-washy postmodern sense, but in a precise, mathematical, experimentally verified sense. Quantum mechanics, taken seriously, erases the line between objective and subjective reality. And that's just the beginning, because once you accept that observers can have incompatible realities, the questions multiply exponentially. If we're having a conversation right now, are we even talking about the same universe? When we remember the past, are we remembering the same past? When we make predictions about the future, are we predicting the same future? Or are we each locked into our own branch of reality, isolated in separate quantum narratives that only occasionally align? Some physicists argue there must be something wrong with this picture, that we're missing a piece of the puzzle, that a deeper theory will restore objectivity and make sense of all this. Others embrace it fully. They say, yes, reality is observer-dependent, and we need to accept that and figure out what it means. Still, others try to find middle ground, arguing that while individual observations might be relative, there's still some underlying objective structure we can point to. But nobody has a satisfying answer. Nobody can tell you definitively what's real anymore. That's the observer problem. Not just that observation affects quantum systems, but that observers themselves are quantum systems. And once you go down that path, once you apply quantum mechanics to the act of observation itself, you discover that reality fractures. It splinters into incompatible perspectives, each one valid, none of them complete. And we're forced to confront the possibility that the universe doesn't have a single definite state. It has as many states as there are observers experiencing it. This is what terrifies scientists, not the math. The math is fine, it's the implications. The realization that everything we thought we knew about reality, that it's objective, consistent, independent of observers, might be fundamentally wrong. Now we arrive at the paradox itself. It's called the Wigner-Deutsch paradox, though it goes by other names depending on who's talking about it. Extended Wigner's friend, the quantum observation paradox. Some just call it the observer disagreement problem. But whatever you call it, it represents one of the most profound challenges to our understanding of reality ever discovered. And unlike earlier quantum paradoxes that could be dismissed as philosophical speculation, this one has been tested. The results are in, and they're terrifying. The setup begins with Eugene Wigner's original thought experiment from 1961, which we touched on earlier. Wigner imagined a friend inside a laboratory measuring a quantum system. From the friend's perspective, the measurement produces a definite result. The quantum superposition collapses, reality becomes concrete. But Wigner is outside the lab, and from his perspective, the entire laboratory, including his friend, is still in superposition. No collapse has occurred yet. Two observers, two different descriptions of reality. Both valid, already problematic. But the modern version takes this much further. In the extended paradox, you don't just have Wigner and his friend. You have four observers arranged in a specific configuration. Two of them, call them Alice and Bob, are inside separate laboratories performing measurements on entangled quantum systems. Two others, call them Charlie and Diane, are outside those laboratories treating Alice and Bob themselves as quantum systems. Here's where it gets interesting. Alice measures her particle and sees a definite result. From her perspective, the superposition collapsed. Bob measures his particle and sees a definite result. From his perspective, his superposition collapsed. But Charlie is looking at Alice's entire laboratory as a quantum system. From his perspective, Alice is in superposition, having measured both possible outcomes simultaneously. And Diane does the same with Bob's lab. Now comes the critical question. Charlie and Diane can perform measurements on Alice and Bob themselves, treating them as quantum objects. When they do, they can verify that Alice and Bob are indeed in superposition. They can confirm quantum interference between the states where Alice saw outcome A and outcome B. From Charlie's perspective, Alice never experienced a single definite result. She experienced both, simultaneously, in superposition. But Alice's memory says otherwise. She remembers seeing one outcome, one definite, concrete result. Not both, never both. So who's right? Did Alice's measurement collapse the wave function, or didn't it? From Alice's internal perspective, yes, she saw a result. Her quantum system collapsed. From Charlie's external perspective, no. Alice is still in superposition. Her measurement hasn't produced a single outcome. And here's the devastating part. Both perspectives are correct according to quantum mechanics. There's no way to say one is right and the other is wrong. They're both valid descriptions of the same physical situation. But it gets worse. Because Alice and Bob's particles are entangled, their measurements are correlated. If Alice sees spin up, Bob should see spin down, according to the rules of quantum entanglement. And from Alice and Bob's perspectives, that's exactly what happens. They compare notes and find the expected correlation. But when Charlie and Diane compare their measurements, they find something different. They find interference patterns that could only exist if Alice and Bob never collapsed into single outcomes. If they remained in superposition the whole time. This isn't just a contradiction between perspectives, it's a contradiction about facts. Did the correlation between Alice and Bob's results exist before Charlie and Diane measured them? Alice and Bob say yes. We saw correlated outcomes. Charlie and Diane say no. The correlation only appeared when we measured the labs. Both pairs of observers have evidence supporting their claims. Evidence that can be physically recorded and verified, yet their claims are mutually exclusive. They can't both be describing the same reality, but quantum mechanics says they are. The mathematical structure of this paradox is remarkably tight. You can write down explicit quantum states for all four observers. You can calculate what each one should measure. You can verify that the predictions are internally consistent from each observer's point of view. But when you try to combine all four perspectives into a single objective description, you can't. The puzzle pieces don't fit together. There's no consistent way to say what actually happened that satisfies all four observers simultaneously. In 2019, physicists Massimiliano Proietti and colleagues published experimental results testing this exact scenario. They didn't use human observers, obviously. They used photons as stand-ins for Alice and Bob, and interferometers as stand-ins for Charlie and Diane. But the quantum logic was identical, and the results matched the theoretical predictions perfectly. Observer A recorded one set of facts. Observer B recorded a different, incompatible set of facts. Both measurements were valid. Both were physically real. Yet they contradicted each other. The implications are staggering. If this is how quantum mechanics works, then facts are not universal. They're local to observers. What happened in the past is not a fixed, objective thing everyone can agree on. It depends on who's asking and from what perspective. Two people can witness the same event and, at the quantum level, experience genuinely different versions of it. Not different interpretations, different actual outcomes, and both versions are real. This demolishes several assumptions we make about reality. First, it destroys observer independence. We usually assume that what happens in an experiment doesn't depend on who's watching. The universe does its thing regardless of observers. But the Wigner-Deutsch paradox says no. Observations are observer-dependent in a fundamental way. Second, it destroys locality of facts. We assume facts are local. If something happens at a specific place and time, it's a fact there, and everyone who checks that location will find the same fact. But if Alice and Charlie can disagree about whether a measurement collapsed, then facts aren't local. They're contextual. Third, and most disturbingly, it suggests reality itself is not a single coherent structure. It's fragmented, shattered into observer-dependent pieces that don't have to fit together. Some physicists have tried to escape this conclusion by rejecting one of quantum mechanics' core assumptions. Maybe superposition doesn't apply to observers, maybe there's a threshold where quantum mechanics stops and classical behavior begins. But every attempt to draw that line has failed. There's no physical principle that says humans or measuring devices can't be in superposition. If quantum mechanics is universal, and all evidence suggests it is, then observers are quantum systems like everything else. And if observers are quantum systems, then the paradox stands. Others suggest that maybe Alice and Bob simply don't have definite experiences while they're in superposition from Charlie and Diane's perspective. Maybe conscious experience only exists in collapsed states, but that creates its own nightmare. It means your experiences, your memories, your sense of existing continuously through time, all of that could be an illusion that only becomes real retroactively when someone outside your quantum system measures you. You wouldn't just be uncertain about reality, you'd be uncertain about whether you're even having experiences at all. Then there's the many worlds interpretation, which says all outcomes happen and reality branches. In that view, Alice sees one result in one branch and a different result in another branch. Both versions of Alice exist. Both are real. The paradox is resolved by saying there's no single reality, just an ever-splitting multiverse. But even that doesn't fully solve the problem because it doesn't explain why you experience one branch and not the others. Why this version of you and not the countless other versions? What makes the Wigner-Deutsch paradox so terrifying isn't just that it breaks our intuitions, it's that it does so in a way that's experimentally confirmed and mathematically rigorous. This isn't philosophy, it's not a matter of interpretation. It's a direct consequence of quantum mechanics applied consistently. If you accept quantum theory, which you must because it's the most successful scientific theory ever created, then you have to accept that reality is observer-dependent. There's no way around it, no escape clause, no hidden loophole that restores objectivity. Let's pause and really think about what we've just encountered, because it's easy to hear these quantum stories and nod along without fully absorbing what they mean. The Wigner-Deutsch paradox isn't saying that people can have different opinions about reality. It's not saying observers have incomplete information. It's saying something far more radical. It's saying that objective facts, the kind of facts that should be true for everyone everywhere, don't exist at the quantum level. And if they don't exist there, we need to ask whether they exist anywhere at all. Think about what a fact is supposed to be. You drop a ball, it falls to the ground. That's a fact. Everyone who was there agrees. Everyone who watches the video agrees. Even someone who wasn't present but hears about it later agrees. The ball fell. That's not perspective dependent. It's not subject to interpretation. It happened. One reality, one consistent history that everyone shares. That's what we mean when we talk about objective reality. Events occur independently of who observes them, and while people might perceive those events differently, the underlying facts remain the same for everyone. Quantum mechanics says that's wrong. Or at least it says that model breaks down when you look closely enough. At the quantum level, there is no single set of facts that all observers must agree on. Alice performs a measurement and gets a result. That's a fact for her. Charlie measures Alice and finds she's in superposition, never having obtained a single result. That's a fact for him. Both facts are physically real. Both can be verified through experiments, but they're incompatible. They describe different realities. And there's no higher court of appeal, no more fundamental level where you can go to find out which one is really true. This creates a philosophical crisis. For centuries, science has been built on the assumption that we're all studying the same universe, that there's an objective reality out there, and our job is to figure out what it is. We might measure it differently, we might use different tools or different theories, but ultimately we're all trying to describe the same thing. The Wigner-Deutsch paradox says that assumption is false. There is no single thing we're all describing. There are only descriptions, and those descriptions don't have to be consistent with each other. Now, you might think, this only matters for tiny quantum systems, particles, photons, things we can't see with our naked eyes. And maybe for everyday objects, facts are still facts, but that's not how physics works. Quantum mechanics isn't a special theory that applies only to small things. It's the fundamental theory. Classical physics, the physics of everyday objects, emerges from quantum mechanics when you average over large numbers of particles. Which means if quantum mechanics allows observer-dependent facts, then classical physics inherits that feature. It just becomes less noticeable because macroscopic objects involve so many particles that the quantum effects wash out. But wash out doesn't mean disappear. It means hidden, averaged, buried under layers of complexity. There are already experiments showing quantum effects at larger and larger scales. Superposition has been demonstrated with molecules containing thousands of atoms. Entanglement has been observed across kilometers. Quantum behavior isn't restricted to microscopic systems. It's just harder to maintain at larger scales because interactions with the environment cause decoherence. But decoherence doesn't solve the measurement problem. It doesn't tell you why one outcome becomes real instead of another. It just explains why quantum effects become harder to see. The fundamental issue remains. Reality is observer-dependent, whether you're measuring a photon or a planet. So what does this mean for our everyday experience? Why do we all seem to agree on basic facts if reality is fundamentally fragmented? The answer is that we're all entangled with the same environment. When you look at a chair, photons bounce off it and hit your eyes. Those photons interact with your brain. That interaction entangles you with the chair's quantum state. When I look at the same chair, the same process happens with me. We both become entangled with the chair in compatible ways, which is why we agree on its properties. But that agreement isn't because the chair has objective properties, it's because our measurements are correlated through shared entanglement with the environment. Think of it like this. Imagine two people looking at the same hologram from slightly different angles. They see similar images because they're looking at the same hologram, but the details differ depending on their viewpoint. Now take that analogy and make it much more extreme. The hologram itself doesn't have a single definite image. It only produces images when someone looks at it. And depending on the exact angle, not just spatially, but in terms of what quantum measurements you perform, you might see completely different images. That's closer to what's happening with quantum reality. The universe doesn't have a single definite state. It has potentials, probabilities, and those probabilities collapse into definite outcomes only from specific observer perspectives. Change the perspective and you change the outcome. This leads to a deeply uncomfortable question. If facts are observer-dependent, what about the past? We normally think the past is fixed. What happened, happened. You can't change it. It's done. But if measurement determines reality and measurements can be made at any time, then in what sense is the past fixed? The quantum eraser experiment already hinted at this. Decisions made now can affect patterns that were recorded earlier, at least statistically. But the Wigner-Deutsch paradox takes it further. It suggests that the past doesn't have a definite form until someone asks about it. And depending on who asks and how they ask, they might get different answers about what happened. That sounds insane. It violates everything we think we know about time and causality. But it's what the experiments show. When Charlie measures Alice's laboratory, he can detect interference between the branches where Alice saw different outcomes. That interference proves both outcomes still exist in superposition from his perspective, which means the past, from Alice's point of view where she saw one outcome, is not the same as the past from Charlie's point of view where she saw both. They're not disagreeing about what happened, they're inhabiting different histories. Some physicists have suggested this means we need to abandon the idea of a single universal timeline. Instead of one past leading to one present leading to one future, we have a branching structure where every observer follows their own timeline. Those timelines can overlap and agree on certain facts, especially at macroscopic scales where decoherence forces consistency. But at the quantum level, the timelines diverge. Your past is not necessarily my past, and neither of us is wrong. This creates another problem. If the past is observer-dependent, then so is causality. We normally think cause comes before effect. You flip a switch, then the light turns on. The flipping causes the illumination. But if different observers have different pasts, then they might disagree about what caused what. From one perspective, event A caused event B. From another perspective, B happened first, or A and B were simultaneous. Or neither caused the other, but both were caused by some third event C that only exists in one observer's timeline. Causality stops being a universal structure and becomes observer-relative. Now, before you completely despair, it's worth noting that these effects only become noticeable when you're dealing with carefully isolated quantum systems. In everyday life, decoherence happens so quickly and so thoroughly that all observers get forced into compatible branches of the wave function. We all see the same macroscopic facts because we're all entangled with the same environment. But that's not the same as saying those facts are objective. It's more like saying we're all trapped in the same illusion. The appearance of objective reality emerges from shared entanglement, not from reality actually being objective. And here's the truly frightening part. If this is correct, then science itself has a problem. Science is supposed to be about discovering objective truths, universal laws that apply everywhere for everyone. But if reality is observer-dependent, then what are scientific laws of? Are they describing the universe as it really is, or are they just describing patterns in our observations? And if different observers can have different patterns, then which observers' patterns are the real laws? Some scientists argue we need to shift our entire understanding of what science is doing. Instead of thinking we're discovering objective reality, we should think of science as building models that predict observations. The models don't have to correspond to some underlying objective truth. They just have to work. They just have to tell us what we'll measure next. This is called instrumentalism, and it's been around for a long time. But the Wigner-Deutsch paradox gives it new weight. If facts really are observer-dependent, then instrumentalism isn't just a philosophical position. It's the only coherent way to do science. That's a huge shift. It means giving up on the idea that we're uncovering the truth about reality. We're not. We're just finding patterns that help us navigate our particular observer-dependent slice of it. Other observers might find different patterns, different laws, different truths. And there's no way to say who's right because there's no objective reality to compare against. There's only what each observer measures. And measurements, as we've seen, don't reveal reality. They create it. This is what keeps quantum physicists up at night, not the equations. The equations are fine. It's the implications. The realization that everything we thought we knew about reality, objectivity, facts, causality, all of it rests on assumptions that quantum mechanics systematically destroys. And we can't just ignore it. We can't pretend the paradoxes don't exist. Because they've been experimentally verified. They're real, which means we have to take seriously the possibility that reality itself, in the way we've always understood it, isn't real at all. We've been dancing around something for a while now, something that makes physicists extremely uncomfortable. If reality depends on observers, then we need to ask what an observer actually is. And that question leads straight into territory most scientists would rather avoid: consciousness. Because if measurements create reality and measurements require observers, then at some point you have to define what counts as an observer. Is it a particle detector, a computer, a bacterium, a human being? Where do you draw the line? And more importantly, why does that line exist at all? This is where the Wigner-Deutsch paradox becomes more than just a physics problem. It becomes a question about the nature of mind itself. Because if you take the paradox seriously, you can't avoid asking whether consciousness plays a fundamental role in shaping reality. Not in some vague, mystical sense, in a concrete, physical sense, the kind that has measurable consequences, the kind that might actually explain why the quantum world behaves the way it does. Let's start with what we know. Quantum systems exist in superposition until measured. Measurement collapses the superposition into a definite outcome. But what counts as a measurement? If you put a particle detector in a box and it registers a particle, has a measurement occurred? Most physicists would say yes. The detector collapsed the wave function. But now ask a harder question. If nobody looks at the detector, if nobody reads its output, is the measurement complete? Or is the detector itself now in superposition, having both detected and not detected the particle? According to the Wigner-Deutsch paradox, the second option is correct. The detector is in superposition until someone observes it. But then we have to ask the same question about that observer. If I look at the detector and see a result, has the measurement chain ended? Or am I now in superposition from the perspective of someone observing me? And if I am, then when does it end? When does reality actually become real? One possible answer is never. The chain of superposition extends infinitely. There's no final observer, no ultimate collapse. Every measurement just entangles the measured system with the measuring device, which gets entangled with the next observer, which gets entangled with the next, on and on forever. This is essentially the many worlds interpretation. Nothing ever collapses, everything just branches. Reality is an infinite tree of possibilities, and every observer experiences one branch while all the other branches exist simultaneously. But there's another answer, one that's more controversial but harder to dismiss than most physicists would like. Maybe the chain ends when it reaches a conscious observer. Maybe consciousness is special, not because it's magical or supernatural, but because it's the one type of physical system that can genuinely collapse a wave function, that can turn possibilities into actualities, that can take quantum superposition and resolve it into classical reality. This idea has a name. It's called the consciousness causes collapse interpretation. And before you dismiss it as pseudoscience, you should know it was taken seriously by some of the founders of quantum mechanics. Eugene Wigner, who created the original thought experiment, believed consciousness was necessary for collapse. John von Neumann, one of the greatest mathematicians of the 20th century, developed a rigorous version of quantum mechanics that required a conscious observer to complete the measurement process. Even Erwin Schrödinger, whose equation describes quantum evolution, was deeply interested in the relationship between consciousness and quantum mechanics. The logic goes like this. If you trace the measurement chain backward, you find that every physical system can be described as quantum mechanical. The particle is quantum, the detector is quantum, the laboratory is quantum, the scientist is quantum. But at some point, something has to observe the whole chain and force it to collapse. Otherwise, the entire universe would remain in superposition forever, and nothing would ever actually happen. So what provides that final collapse? What's the system that's outside the quantum chain looking in? The answer, according to this interpretation, is consciousness, not the brain. The brain is physical, it's made of atoms, it's quantum mechanical like everything else. But consciousness itself, the subjective experience of being aware, might be fundamentally different. It might be the interface between the quantum world of possibilities and the classical world of definite outcomes. When a conscious being observes a quantum system, the wave function collapses, not because of any physical interaction, but because consciousness is the thing that actualizes reality. Now, this immediately raises 1,000 questions. What counts as conscious? Are animals conscious enough to collapse wave functions? What about insects, single-celled organisms? Where's the threshold? And more fundamentally, what is consciousness? If it's not just brain activity, if it's something separate that can act on physical systems, then what is it made of? How does it interact with matter? Why don't we see it directly in our equations? These are hard questions, and most physicists avoid them by rejecting the premise. They say consciousness has nothing to do with quantum mechanics. Collapse happens through decoherence, through interaction with the environment. Consciousness is just along for the ride, experiencing whatever outcome happens to occur in its branch of the wave function. But the Wigner-Deutsch paradox makes that position harder to maintain. Because if observers can disagree about objective facts, then something has to determine which observer's perspective is correct. And if there's no objective reality to appeal to, then the only thing left is the subjective perspective of the observer, which brings us right back to consciousness. Here's why this matters. If consciousness really does play a role in collapsing quantum states, then the universe isn't just a mechanical system evolving according to fixed laws. It's a participatory system. Reality emerges from the interaction between quantum possibilities and conscious observers, which means you're not just a passive witness to reality, you're actively creating it every time you make an observation. Every time you become aware of something, you're collapsing wave functions, turning potentials into actualities, shaping the universe in ways that wouldn't happen without you. That sounds empowering, but it's also deeply disturbing, because it means reality is fundamentally unstable. It's constantly being created and recreated by countless conscious observers, all collapsing wave functions in slightly different ways. And if those collapses don't have to agree with each other, then we're back to the same problem. Observer-dependent reality, multiple incompatible versions of events, a universe that fractures along the lines of consciousness itself. Some physicists have tried to formalize this idea. Roger Penrose, a Nobel Prize winner, has proposed that consciousness emerges from quantum processes in the brain that resist decoherence long enough to create integrated conscious experiences. He suggests that consciousness involves a kind of objective reduction of the wave function, a physical collapse that happens when quantum superpositions reach a certain threshold. His theory, developed with anesthesiologist Stuart Hameroff, locates this process in structures called microtubules inside neurons. It's controversial. Many neuroscientists reject it. But it's a serious attempt to connect consciousness with quantum mechanics in a testable way. Others have gone further. Physicist Henry Stapp argued that consciousness is necessary to explain the results of quantum experiments. He claimed that the act of choosing what to measure, which is a conscious decision, affects the quantum state before the measurement even happens. In his view, free will and quantum mechanics are intimately connected. The choices conscious beings make don't just reveal reality, they help determine it. The future isn't fixed. It's shaped by conscious decisions interacting with quantum possibilities. Now, most physicists find these ideas uncomfortable. They sound too much like mysticism, too much like saying the universe cares about us or that our thoughts have magical powers. But the discomfort comes from a bias toward materialism, toward the assumption that consciousness is just a byproduct of physical processes with no causal power of its own. That assumption might be wrong. And the Wigner-Deutsch paradox gives us a reason to question it. Because if observers really can have different realities, and if there's no objective way to reconcile those realities, then the observer's subjective perspective becomes fundamental. And subjective perspective is just another word for consciousness. There's also experimental work being done to test whether consciousness affects quantum systems. It's difficult because consciousness is hard to define and even harder to measure, but some researchers have looked at whether human intention can influence random quantum processes. The results are mixed and controversial. Most physicists dismiss them as statistical noise or experimental error. But a small group argues there's a real effect, small but measurable, suggesting that conscious observation does something more than passive recording. Even if those experiments are wrong, even if consciousness has nothing to do with collapse, the Wigner-Deutsch paradox still forces us to confront the observer problem. Something has to determine when and how reality becomes definite. If it's not consciousness, then what is it? Where does the chain of quantum entanglement end, or does it never end? And if it never ends, then in what sense is anything real? These aren't easy questions. They sit at the boundary between physics, philosophy, and neuroscience. They demand that we think carefully about what we mean by observation, measurement, reality, and experience. And they remind us that quantum mechanics, for all its mathematical precision, still doesn't tell us what's actually happening. It tells us what we'll observe, but it doesn't tell us what we are, or why our observations matter, or whether the act of experiencing something brings it into existence. What makes this so terrifying is that we can't escape it by ignoring consciousness. The moment you take quantum mechanics seriously and apply it to observers themselves, consciousness becomes unavoidable. Because observers are the things that have experiences, and experiences are the only direct access we have to reality. Everything else is inference, theory, calculation. But the raw fact of awareness, the undeniable reality of subjective experience, that's where quantum mechanics and consciousness collide. And we still don't know what happens at that collision point. We just know it's where reality, whatever that word means, gets made. Here's a question that seems simple until you think about it too carefully. Are you the same person you were 5 minutes ago? Most people would say yes without hesitation. Of course you're the same person. You have continuous memories. Your body hasn't changed in any meaningful way. You feel like yourself. There's a clear sense of identity that persists through time. That's what it means to be you, a continuous self that exists from moment to moment, experiencing life as a unified whole. But the Wigner-Deutsch paradox suggests that picture might be wrong, deeply wrong, because if reality is observer-dependent, and if different observers can experience incompatible versions of the same events, then what does it mean for you to be a continuous self? If the version of you that exists from one observer's perspective is in superposition, experiencing multiple outcomes simultaneously, while the version of you from your own perspective experienced only one outcome, then which version is really you? Or are they both you? And if they're both you, then are you really one person, or are you many? Let's make this concrete. Imagine you're in a laboratory about to measure a quantum system. From your perspective, you press the button, the measurement happens, and you see a result. Let's say the particle is spin up. That's your experience, that's your memory, that's your reality. As far as you're concerned, that's what happened. One outcome, one definite fact. But now imagine someone outside the laboratory observing you as a quantum system. From their perspective, you're in superposition. You pressed the button and saw spin up, and you pressed the button and saw spin down. Both versions of you exist simultaneously in different branches of the wave function. So which one is you? The version that saw spin up, the version that saw spin down? Or are you somehow both at once, even though from your internal perspective you only experienced one? This isn't just an abstract puzzle, it touches on something fundamental about personal identity. The sense that there's a single, continuous you experiencing reality in a linear way. If that sense is an illusion, if there are actually multiple versions of you branching off at every quantum event, then what does that mean for everything you think defines you? Your memories, your decisions, your sense of being a unified self? The many worlds interpretation makes this problem explicit. In that view, every quantum measurement splits the universe into multiple branches. In each branch, a different version of you experiences a different outcome. All those versions are equally real. They all think they're the one true you. They all have memories that feel continuous and consistent. But they're living in different realities, experiencing different pasts and different futures. So when you make a quantum measurement, you're not just discovering which outcome occurred. You're splitting into multiple copies, each one experiencing a different outcome, and all of them convinced they're the original. That raises a disturbing question. If you split every time a quantum event occurs, how many copies of you exist right now? Quantum events happen constantly. In your brain, in your body, in the environment around you, every single one creates a branching point, which means the number of copies of you is growing exponentially every fraction of a second. Trillions upon trillions of versions, all slightly different, all experiencing slightly different realities. And there's no way to say which one is the real you because they're all equally real. Now, most versions are nearly identical. The differences are microscopic, buried in the quantum noise of atomic interactions. But some branches differ significantly. In one branch, you decided to have coffee this morning. In another, you had tea. In another, you skipped breakfast entirely. Those versions of you made different choices, had different experiences, and are now living in different personal histories. Are they still you, or are they different people who happen to share most of your memories? This gets even stranger when you consider that these branches can interfere with each other under the right conditions. If you're put into a quantum superposition from someone else's perspective, then the different versions of you can exhibit quantum interference. They can affect each other in ways that single classical objects can't, which suggests that personal identity isn't a simple, linear thing, it's a quantum phenomenon. You're not one person moving through time, you're a superposition of possibilities, constantly branching and interfering, creating the illusion of a single, continuous self. Some philosophers have tried to make sense of this by arguing that personal identity is not about being the same physical entity over time. It's about continuity of experience. As long as your memories connect smoothly from one moment to the next, you're the same person, even if you're technically a different physical configuration or a different branch of the wave function. This is called the psychological continuity theory. Through and if those branches become more and more improbable, the world around you might become increasingly bizarre, filled with unlikely coincidences that just happen to keep you alive. This isn't just science fiction, it's a logical consequence of taking many worlds seriously and asking what happens to personal identity in a constantly branching universe. You might object and say that this only matters for quantum events, and most of life is classical. But remember, quantum mechanics is fundamental. Classical behavior emerges when quantum effects average out. But the branching still happens, it just becomes invisible because the branches decohere and stop interfering with each other. But invisible doesn't mean non-existent. The other branches are still there. Other versions of you are still experiencing different realities, you just can't access them. Now, if you reject many worlds, the problem doesn't go away. It just changes form. If you think the wave function genuinely collapses, then you have to ask what happens to the other possibilities. If you measured spin up, what happened to the version of reality where the particle was spin down? Did it never exist? Or did it exist briefly in superposition before being erased when the collapse occurred? And if it was erased, what does that say about the nature of existence? That possible futures can be real for a moment before being retroactively deleted when one outcome gets selected? Either way, the continuity of self becomes questionable. If you're constantly splitting into branches, then there's no single you. If you're not splitting but possibilities are being erased, then parts of potential, you are being destroyed at every moment. Neither option preserves the naive idea that you're a single, continuous entity moving through a single, continuous timeline. Quantum mechanics, regardless of interpretation, fractures the self. Some physicists argue this doesn't matter for practical purposes. Yes, the quantum description is strange, but at the level of conscious experience, we perceive ourselves as unified. The quantum effects wash out. We never feel ourselves splitting or interfering or superposing. We just experience one continuous stream of consciousness, one moment after another. And maybe that's enough. Maybe the unity of self is an emergent property, something that appears at the macroscopic level even though it doesn't exist at the quantum level. But that's cold comfort if you're trying to understand what you actually are. Because if the unity is just an illusion, just a useful approximation that breaks down when you look closely, then what are you really? A temporary pattern in a wave function? A branch in an ever-expanding tree of possibilities? A localized collapse in an otherwise infinite superposition? None of these answers feel satisfying. None of them match the direct, undeniable experience of being a single, continuous person. And this is where the Wigner-Deutsch paradox becomes personal. It's not just about particles or laboratories or abstract observers, it's about you, your identity, your sense of existing continuously through time. The paradox suggests that sense might be fundamentally misleading, that the self you experience is not a unified, objective entity, but an observer-dependent construct that exists differently from different perspectives. You think you're one person, but from a quantum perspective, you might be many, or none, or something else entirely that we don't have words for yet. What makes this terrifying is the erosion of certainty about the most basic thing you know, your own existence. You can doubt the external world. You can question whether other people are conscious. You can wonder whether you're in a simulation or a dream. But the one thing that seems absolutely certain is that you exist. You're having experiences right now. There's something it's like to be you. That's the foundation everything else rests on. But if quantum mechanics is right, even that foundation is shaky. because the you that exists depends on who's observing you. And from some perspectives, you might not exist as a single entity at all. This brings us back to consciousness, because whatever else you are, you're a conscious being having experiences. And those experiences feel unified and continuous. That unity has to come from somewhere. Either it's real, in which case consciousness might be the thing that holds the self together across quantum branches. Or it's an illusion, in which case consciousness itself is more fragmented than it appears. Either option is unsettling. Either consciousness is doing something special, holding reality together in a way physics can't explain, or consciousness is fooling itself, constructing a false sense of unity over an underlying fragmentation it can't perceive. The Wigner-Deutsch paradox doesn't answer these questions, it just makes them unavoidable. It forces us to confront the fact that the self, the observer, the you that's reading these words right now, is not a simple, well-defined entity. It's something strange and quantum and observer-dependent, something that might exist in multiple, incompatible ways simultaneously, something that might not even be a single thing at all. Memory feels reliable. You remember what you had for breakfast, you remember conversations from yesterday, you remember your childhood, your education, the major events of your life. Those memories might fade or distort over time, but they feel like records of things that actually happened, a personal history that's yours and yours alone. But if the Wigner-Deutsch paradox is correct, that intuition might be completely wrong. Because if reality is observer-dependent, then so is the past. And if the past is observer-dependent, then your memories aren't records of what happened. They're records of what happened from your perspective, which might not be what happened from someone else's perspective, or what happened at all, in any objective sense. Let's think about what memory actually is in physical terms. A memory is a pattern stored in your brain. Neurons connected in specific ways, chemical traces, electrical activity that encodes information about past experiences. When you remember something, your brain reconstructs that pattern. It doesn't play back a recording. It rebuilds the experience based on traces left behind. That reconstruction process is imperfect. Memories change, details get added or removed. Emotions color the recollection. This is well-established psychology. Memory is constructive, not reproductive. But quantum mechanics adds another layer of strangeness. If you were in superposition during the event you're remembering, then from some observer's perspective, you experienced multiple outcomes simultaneously. Different versions of you encoded different memories. And when the superposition collapsed, one set of memories became yours. But the collapse is observer-dependent, which means different observers might see you as having different memories of the same event. From your internal perspective, you remember one thing. From an external observer treating you as a quantum system, you remember multiple contradictory things simultaneously. This isn't just theoretical. In the Wigner-Deutsch setup, Alice measures a particle and forms a memory of the result. From her perspective, she remembers seeing a specific outcome. But Charlie, observing Alice as a quantum system, can verify that Alice is in superposition between two different memory states. She simultaneously remembers seeing spin up and spin down. Both memories exist. Both are physically encoded in her brain. But from Alice's subjective perspective, only one is accessible. She can't experience both memories at once. She only experiences the one corresponding to her branch of the wavefunction. So what is the truth about what Alice experienced? She says she saw one outcome. Her memory confirms it. But the physical state of her brain contains both memories. They're both there, encoded in superposition. From Charlie's perspective, neither memory is more real than the other. They're both part of Alice's quantum state, but from Alice's perspective, only one is real. The other doesn't exist for her. It's not a faded memory or a forgotten experience. It's literally not part of her conscious awareness. This creates a bizarre situation. Your memories are supposed to tell you what you experienced. They're your personal record of your own past. But if you can be in superposition, then your physical brain contains memories you don't have access to. Experiences you went through from some observer's perspective, but that aren't part of your conscious history. You remember one version of events. But another observer looking at your brain quantum mechanically sees that you simultaneously remember multiple incompatible versions. Now extend this to your entire life. Every time you've made an observation, every time you've interacted with a quantum system, which is constantly, you've potentially branched. Different versions of you experience different outcomes and form different memories. Most of these branches are nearly identical. The differences are microscopic, but they're there. Which means your memory, the thing you think of as your personal history, is actually just one branch in an enormous tree of possibilities. Other branches contain other versions of you with other memories. And all those memories are equally valid. They're all physically encoded in quantum states, even if you only have conscious access to one set. This raises a disturbing question. Are your memories even yours? If there are countless versions of you with slightly different memories, all branching from the same starting point, then what makes your specific set of memories special? Why are these memories the ones you experience instead of the others? Is it just random, or is there something about your conscious perspective that selects one branch over the others? The problem gets worse when you consider that memories can be affected by future measurements. In the delayed choice quantum eraser, the pattern you see depends on decisions made after the photons hit the screen. The past, in a sense, gets determined by the future. Applied to memory, this suggests that your recollection of past events might depend on future observations. Not in a time travel sense, but in a quantum sense. The full history of what you experienced might not be determined until all the quantum measurements in your causal future are complete, which means your past is constantly being updated, revised, completed by observations you haven't made yet. That sounds impossible, but it's what the experiments show. Quantum systems don't have definite histories until you ask about them, and asking at different times or asking in different ways can yield different answers about what happened. Applied to human memory, it suggests that your past isn't fixed, it's fluid, context-dependent, subject to revision based on how you interact with it. Some researchers have suggested that memory itself might be a quantum process, that the brain uses quantum coherence to store and retrieve information in ways that classical systems can't. This is controversial. Most neuroscientists think the brain is too warm and wet for quantum effects to matter. Decoherence happens too quickly. But there's some evidence that quantum processes might play a role in certain neural functions. Photosynthesis uses quantum coherence. Bird navigation might rely on quantum entanglement in the retina. Why not memory? If memory is quantum, then it's subject to all the same paradoxes: superposition, entanglement, observer dependence. Your memories wouldn't be simple records stored in neurons. They'd be quantum states that exist in superposition until accessed. And accessing them would be a measurement, which means it would collapse the superposition into one outcome, which means the act of remembering would determine what you remember, not reveal it, determine it. Think about what that implies. When you recall a memory, you're not retrieving a fixed record. You're collapsing a quantum superposition of possible memories into one definite recollection. And that recollection depends on how you access it, what you're thinking about when you try to remember, what context you're in, what questions you're asking yourself. All of those factors could influence which branch of the memory superposition collapses, which version of the past becomes real for you in that moment. This would explain some strange features of memory that psychologists have documented. False memories, memories that change each time you recall them. The way leading questions can alter what someone remembers. If memory is quantum, these aren't just psychological quirks. They're fundamental features of how memory works. Because memory isn't about accessing the past. It's about creating the past through measurement. Now, most of this is speculative. We don't have proof that memory is quantum. We don't know if human brains can maintain quantum coherence long enough for it to matter. But the Wigner-Deutsch paradox tells us it's at least possible. Because if observers can be quantum systems, then everything about observers, including their memories, is quantum. And if memories are quantum, then the past is observer-dependent, just like the present. Here's where it gets truly unsettling. If your memories are observer-dependent, then you can't trust them as objective records. You remember things from your perspective, but someone else observing you as a quantum system might see that you remember something different, or multiple contradictory things. Your internal narrative, the story you tell yourself about who you are and what you've experienced, is just one branch, one possibility. Other branches have other stories. And there's no way to say which story is true because truth itself is observer-dependent. This undermines one of the foundations of personal identity. We define ourselves through our memories. Who you are is largely a function of what you've experienced, but if what you've experienced is observer-dependent, then who you are is also observer-dependent. You're not a fixed entity with a definite history, you're a superposition of possibilities, and which possibility you experience depends on how you're observed. That has profound implications for concepts like responsibility, continuity, and selfhood. If the past is malleable, if memories are created rather than retrieved, then the foundation of personal identity shifts. You're not the sum of your experiences because your experiences aren't fixed. They're quantum, probabilistic, observer-dependent. The person you were yesterday might not be the person you remember being today, not because your memory is faulty in the ordinary sense, but because the past itself has changed. Some philosophers have embraced this radical uncertainty. They argue that the self is always constructed, always in flux, and quantum mechanics just makes that explicit. Others recoil from it. They insist there must be some objective fact about what you experienced, even if we can't access it directly. But the Wigner-Deutsch paradox doesn't give us that comfort. It tells us there is no objective fact, there are only perspectives, and perspectives can contradict each other while both being correct. What does that mean for living your life? If you can't trust your memories, if the past is fluid, if your experiences depend on who's observing you, then how do you make decisions? How do you learn from experience? How do you maintain any sense of consistency or meaning? These aren't just philosophical questions, they're practical problems that arise directly from taking quantum mechanics seriously and applying it to conscious observers. The terrifying answer might be that you can't. That coherence and meaning are illusions we construct to make sense of a fundamentally incoherent universe. That the unity of self and the solidity of memory are approximations that work well enough at macroscopic scales but break down completely when you look at the quantum level. And if that's true, then everything you think you know about yourself is suspect. Not just uncertain, fundamentally questionable, because you're not a thing with a history. You're a process with many possible histories, and which one is yours depends on how you're measured. For decades, the Wigner-Deutsch paradox existed purely as a thought experiment, something physicists discussed in conference rooms and argued about in papers, but nothing anyone could actually test. The scenarios involved treating human observers as quantum systems, putting laboratories into superposition, measuring consciousness itself. Impossible, or so it seemed. But in the last few years, that changed. Physicists found clever ways to translate the paradox into experimentally testable predictions. And when they ran those experiments, the results were exactly as disturbing as the theory predicted. The breakthrough came from realizing you don't need actual human observers. You just need quantum systems that can store information and play the role of observers in the paradox. Photons work perfectly. They can be entangled, put into superposition, measured, and used to encode information about other quantum systems. So researchers designed experiments where photons acted as Alice and Bob, the observers inside the laboratories, while other quantum operations acted as Charlie and Diane, the external observers. In 2019, a team led by Massimiliano Proietti at Heriot-Watt University published results in Science Advances that sent shockwaves through the physics community. They created a quantum system with 4 entangled photons arranged in the exact configuration the paradox requires. 2 photons played the role of the quantum systems being measured. 2 others played the role of the internal observers, Alice and Bob, making measurements. And then the researchers themselves acted as the external observers, Charlie and Diane, performing measurements on Alice and Bob. The setup was elegant. They used beam splitters and interferometers to create superpositions and extract quantum information without fully collapsing the states. This let them verify something extraordinary. From Alice and Bob's perspective, represented by the photons playing their roles, definite measurements had occurred. The results were recorded. Reality had collapsed into specific outcomes. But from Charlie and Diane's perspective, Alice and Bob were still in superposition. No definite measurements had happened. Both outcomes existed simultaneously. And here's the crucial part. When Charlie and Diane performed their measurements, they found quantum interference. interference that could only exist if Alice and Bob had remained in superposition throughout the entire process. But if you looked at Alice and Bob's recorded data directly, you'd see definite results. One outcome, not both. The paradox wasn't just theoretical anymore. It was sitting there in the lab producing actual data that confirmed the disturbing predictions. The researchers went further. They calculated something called the Wigner's friend inequality. This is similar to Bell's inequality, which tests for local realism in quantum mechanics. The Wigner's friend inequality tests whether you can maintain three assumptions simultaneously. Physical reality is independent of observation, measurements have single outcomes, and choices made by observers are free. If quantum mechanics is correct, you can't have all three. Something has to give. The experimental results violated the inequality dramatically. The data showed that at least one of those assumptions is false. Either reality depends on observation, or measurements don't have single outcomes, or free choice is an illusion. There's no way to keep all three and still match what the experiments show. This isn't about interpretation anymore, it's about what's actually happening in controlled laboratory conditions. Other research groups quickly replicated and extended these results. A team in China performed a similar experiment with even higher precision. Another group at the University of Vienna tested different configurations of the paradox and found the same violations. The consistency was stunning. Every careful test confirmed that observers can record incompatible facts about the same quantum event, and both be correct within their own reference frames. But the experiments also revealed something the theory hadn't fully emphasized. The degree of violation increases with the complexity of the quantum system. Simple two-level systems show small violations. But as you add more particles, more entanglement, more layers of observation, the violations grow. This suggests that the observer dependence of reality isn't just a tiny quantum effect that averages out at large scales. It scales up, which means the paradox potentially applies to larger and larger systems as quantum technology improves. There was also an experiment in 2020 that tested a different aspect of the paradox. Instead of using photons, researchers at MIT used superconducting qubits, the same kind used in quantum computers. These qubits can be carefully controlled and measured in ways that reveal their full quantum state. The team created a scenario where one qubit measured another, then a third system measured both. They found the same pattern. The first qubit recorded a definite outcome from its own perspective, but remained in superposition from the third system's perspective. What made this experiment particularly striking was the ability to read out the qubit states directly. You could see in the data that the first qubit had information about the measurement. It had, in a real physical sense, observed something and recorded the result. But that information existed in superposition. The qubit simultaneously held both possible measurement outcomes. And depending on how you interrogated it, you get different answers about what it had measured. These experiments answer a lot of skeptical questions. People used to say maybe the paradox only exists in theory, maybe real systems don't behave that way, maybe there's some physical principle we're missing that prevents the contradictions. But the experiments close those loopholes. Real quantum systems in real laboratories producing real data confirm the paradox. Observers genuinely do record incompatible realities. That's not speculation, it's measurement. The implications hit the scientific community hard. These weren't fringe results published in obscure journals. They appeared in top-tier publications, peer-reviewed by leading physicists, replicated by independent teams. The paradox was real, which meant its consequences were real too. Objective reality, at least in any traditional sense, couldn't be maintained. Something fundamental about how we understand the world had to change. Some physicists responded by doubling down on many worlds. They said, look, this is exactly what we predicted. All outcomes happen, observers split into branches, each branch is real. The experiments just confirm it. Others leaned into relational quantum mechanics, the idea that quantum states are always relative to an observer. There's no absolute state, just relationships between systems. The experiments fit that picture too. But a significant number of physicists simply didn't know what to make of it. The results were clear, but the interpretation remained murky. If you asked 10 quantum physicists what the Wigner-Deutsch experiments proved, you'd get 10 different answers. They all agreed the experiments worked and the results were significant. But they disagreed profoundly about what it meant for reality. What's particularly important is that these experiments aren't the end, they're the beginning. Research groups around the world are now designing more elaborate tests, experiments with biological molecules to see if quantum observer effects apply to complex organic systems, experiments with larger objects to push the boundary of where quantum behavior stops, experiments specifically designed to test whether consciousness plays any role by using different types of measuring devices and seeing if the results depend on the complexity of the observer. There's even talk of experiments involving actual human observers in controlled quantum scenarios, not putting people in superposition, which is still impossible, but creating situations where human decisions about what to measure affect quantum systems in ways that test observer dependence. These experiments are ethically and technically challenging, but they're being seriously discussed because the stakes are so high. The experimental confirmation of the Wigner-Deutsch paradox represents a turning point. For over a century, quantum mechanics has been weird in theory. Now it's weird in practice in ways we can't ignore. The paradoxes aren't just mathematical curiosities, they're features of reality that show up when you build the right experiments. And that means we have to take them seriously. We have to confront what they're telling us about the nature of existence, observation, and truth. What terrifies scientists isn't the complexity of the math or the difficulty of the experiments. It's the clarity of the results. There's no ambiguity, the data is clean, the violations are significant, and the conclusion is unavoidable. Reality, as we've understood it for centuries, doesn't work the way we thought. Observers aren't separate from the systems they observe. Facts aren't universal. Truth isn't objective. And we can prove it in a laboratory with equipment you could fit on a table. That's why these experiments changed everything. They moved the conversation from philosophy to physics, from speculation to measurement, from what if to this is what we found. And what we found is that the universe is stranger, more fluid, and more observer-dependent than anyone wanted to believe. The experiments didn't just confirm a paradox, they confirmed that reality itself is paradoxical. And we have to figure out how to live with that knowledge. There's a concept that sits at the foundation of all science. It's so basic, so obvious, that most scientists never even think to question it. The idea is simple. There's a real world out there, independent of us, and our job is to study it. When two scientists in different laboratories perform the same experiment, they should get the same results because they're both measuring the same objective reality. If they get different results, one of them made a mistake, or there's some variable they didn't control for. But fundamentally, there's one truth out there, and science is the process of discovering it. The Wigner-Deutsch paradox destroys that idea completely. It doesn't just challenge it or complicate it, it demonstrates through rigorous mathematics and experimental confirmation that objective reality in the traditional sense doesn't exist. There is no single truth that all observers must agree on. There are only observer-dependent truths, and those truths can contradict each other while both being perfectly valid. This isn't a problem we can solve with better experiments or more careful analysis. It's a fundamental feature of how the universe works. Let's be clear about what objectivity means in science. When we say something is objective, we mean it exists independently of who's observing it. The mass of an electron is objective. Every physicist who measures it gets the same answer with an experimental error. The speed of light is objective. It doesn't matter who measures it or where they are. The laws of physics are supposed to be objective. They apply the same way everywhere, for everyone. That's what makes science possible. We're all studying the same universe, so we can compare results and build on each other's work. But quantum mechanics, particularly through the Wigner-Deutsch paradox, says that objectivity breaks down at the fundamental level. When you perform a quantum measurement, what you observe depends not just on the system being measured, but on your relationship to that system. Are you inside the experiment or outside it? Are you entangled with the system or isolated from it? Your position in the web of quantum correlations determines what you see, and different positions can yield genuinely different results. This goes beyond the usual observer effects in physics. Yes, in relativity, different observers moving at different speeds see different things. Time dilation, length contraction, relativity of simultaneity. But there's still an objective space-time structure that everyone agrees on. You can transform between reference frames and reconcile the differences. There's still one reality, just viewed from different angles. The Wigner-Deutsch paradox is different. There's no transformation that reconciles the different observers' results. They're reporting fundamentally incompatible facts about the same event, and both are correct. Some scientists have tried to save objectivity by restricting it. Maybe objectivity exists at the macroscopic scale but breaks down at the quantum level. Maybe observer dependence only matters for carefully isolated quantum systems, not for everyday objects. But that's a retreat, not a solution. Because if objectivity fails at the fundamental level, then it's not truly fundamental. It's an approximation that works in certain regimes. And approximations, by definition, aren't the whole truth. Others argue that we need to redefine objectivity. Maybe we can't have observer-independent reality, but we can have something weaker. Intersubjective agreement. The idea that while reality might depend on observation, observers who interact with the same environment will reach consistent conclusions. This preserves some form of shared truth without requiring that truth to exist independently of all observers. But even that weaker version has problems. The Wigner-Deutsch paradox shows that observers don't always reach consistent conclusions. Alice and Charlie observe the same quantum system and record different facts. Their conclusions aren't just different perspectives on the same underlying reality. They're contradictory claims about what happened, and quantum mechanics says both are right, so even intersubjectivity fails at the quantum level. The philosophical implications are staggering. For centuries, philosophy has debated whether reality exists independently of the mind. Realists say yes, there's an external world that exists whether anyone perceives it or not. Idealists say no, reality is fundamentally mental, and the physical world depends on consciousness. Most scientists have been implicit realists. They assume there's a physical world out there doing its thing regardless of observers. The Wigner-Deutsch paradox suggests the idealists might have been onto something. Not in a mystical sense, but in the precise sense that quantum mechanics requires observers to actualize definite outcomes. This creates a crisis for philosophy of science. The entire scientific method is built on the assumption of objectivity. Experiments should be reproducible. Different researchers should get the same results. Theories should make predictions that everyone can verify. But if reality is observer-dependent, then reproducibility becomes context-dependent. Two researchers might perform the exact same experiment and get different results if they're in different quantum states relative to the system being measured. And both results would be correct. You might think this would make science impossible. How can you build knowledge if there's no objective truth to discover? But science continues to work, even in the quantum realm. We build quantum computers, quantum communication systems, quantum sensors. The technology functions, so clearly there's something we can rely on, even if it's not objectivity in the traditional sense. What we're left with is something more subtle. Quantum mechanics gives us precise, reliable predictions about what observers will measure in specific contexts. It tells us the probabilities of different outcomes, the correlations between entangled systems, the interference patterns that emerge under certain conditions. All of that is reproducible and testable. But it doesn't tell us what exists independently of observation. It only tells us what observations will reveal, and that's a profound shift. Some physicists call this instrumentalism, the view that scientific theories aren't descriptions of reality. They're tools for predicting observations. In this view, we should stop asking what the wave function really is, or whether particles really exist in superposition. Those questions assume there's an observer-independent reality to discover. Instead, we should just use quantum mechanics as a computational tool. It tells us what we'll see when we look.